Hi everybody, we are in our third unit on periodic table and it is Tuesday 10/6. Just a couple of things before we get started. A reminder that your third exam on periodic table is this Friday. To kind of help you with this, there's a Quizlet study set for Unit 3 that is available in the Schoology resources folder. So it has a number of different terms and things we've talked about so far. If you are in period 7 only, you are going to turn in your lab number 8, which is your aliens lab. That's due today. You're going to take out your reference table and your gold Unit 3 note packet. And then your homework tonight. If you are in periods 2 and 5 only, that aliens lab is due tomorrow. If you are in period 7 only, the lab you do next period, Coulombs law, that will be due on Thursday. And then the other homework is your Unit 3 exam, which is on Friday. So once again, periods 2 and 5, finish that aliens lab. Period 7, finish that Coulombs law lab that you'll be doing next period. So what I want you to do is we're going to do a couple of warm-up questions. You may do this on the back of your note packet if you would like. So here are the 3 warm-up questions I would like you to answer, and you do need a periodic table in order to do these. The first is I would like you to draw a Lewis dot diagram for an ion of bromine. So I want you to think about when bromine forms an ion, what type of ion does it form, and what would the Lewis dot diagram look like for that? For number 2, on the periodic table, an element is classified as a semi-metal or metalloid, can be found in which period and which group? So this is a multiple choice. And then for number 3, in which area of the periodic table are the elements with the strongest non-metallic properties located? So I'd like you to pause the video and then give everybody about 4 minutes to try to answer these questions and then replay. Okay, so let's start with number 1. It says to draw a Lewis dot diagram for an ion of bromine. So let's take a look at bromine right here. Bromine is in group 17. That means it has 7 valence electrons. Remember, the magic number for a stable electron configuration is 8. So that means bromine needs to gain 1 more electron to have a stable electron configuration. So we would say that bromine likes to form a -1 ion to get 1 more electron. And if you remember from last unit, when we have a negative ion, we show 8 dots to show those 8 valence electrons. We draw brackets and then a charge. Bromine likes to gain 1 electron, so it's a negative charge. Remember, if it's a positive ion, we draw no valence electrons, brackets, and the positive charge. All right, for number 2, on the periodic table, an element that is classified as a semi-metal or metalloid can be found where? So remember, there's a phrase to help you remember your semi-metals or metalloids. It's big, silly, gerbils are stupid teleporters, por favor. And those are found along that staircase, which is in this bold black. So if we take a look in period 2, which is row 2, group 14, column 14, that's carbon. That's not a metalloid. If we do the next one, we have period 3, group 16, that is sulfur. That is also not a metalloid. It's a nonmetal. Then we have period 6, group 14s. That's row 6, column 14. That is lead. That is a metal. That is not a metalloid. And then we finally have period 4, so row 4, group 15. That is arsenic. That is a metalloid. So for this one, choice 4 is the correct response. And then finally, for the third one, in which area of the periodic table are elements with the strongest non-metallic properties located? So remember, your metals are to the left of the table. So that is everything excluding hydrogen. So your most metallic is the bottom left, and then your non-metals are to the right-hand side. And your most non-metallic is going to be the upper right. That is going to be fluorine is the most non-metallic. Group 18, those don't like to react, so we actually say that fluorine is the most non-metallic. So for strongest non-metallic, that would be choice 4, the upper right. So those are just a few review questions based on what we did in class yesterday. What we're going to do now is you're going to take your notes out to page 8. and we're going to start talking about some periodic trends. Today we'll talk about Coulombs law, which you're going to get a lab about, and then we'll talk about atomic radius and ionic radius. So you are going to need your reference table turned to the periodic table. So we're going to start with Coulombs law. So there are a number of characteristics that will show specific trends or patterns as we go down a group and across a period. You kind of saw that when we looked at valence electrons and energy levels. Remember, as you go down a group, valence electrons stay the same and number of energy levels increased, and then left to right across the period, the valence electrons increase and the energy levels stay the same. So remember, atoms contain charged particles. They have our protons and our electrons. So it's useful to look at the interactions of these charged particles before we actually start to look at those trends and properties of an atom. We can use a mathematical model to help us interpret how strongly the nucleus attracts to different electrons in an atom. Now, don't be alarmed. You're not going to be doing any quantitative calculations with this. These are all going to be qualitative. And if you take a look, this is Coulomb's law. And this equation is actually taken directly from the back page, page 4 of your reference table. So if you take a look, this is page 4. Right here, I took that right out of there. And notice it says qualitative analysis. And it gives you what each symbol represents. So we're going to go through that and look at what it means. So let's make a little note. This is found on page 4 of your reference tables. So let's look at each of these variables and then we'll kind of divulge what they mean. So F on here, this stands for Coulombic force. Sometimes we call it an electrostatic force. That's the force. Q1 and Q2. Q stands for charge. Q1 stands for the charge of the first particle and Q2 stands for the charge of the second particle. So Q is charge of your particles. And then D is the distance of separation between your two particles. So we're going to do distance between particles. All right, so we have force, we have the charge of the particles, and the distance between the particles. So now let's look at how each of those variables is kind of listed in this equation. So here we have F, that's our force, and then it's this symbol. This symbol means proportional to. So this just means proportional to. And we have Q1 times Q2 on the top, and then D squared on the bottom. So how do we really look at this? Well, the force is directly proportional to the charge. So we're going to write directly proportional to the charge. So what does directly proportional to the charge mean? Well, that means the larger the charge carried by each particle, the greater the force. So notice, that's why Q1 and Q2 are in the numerator. So the higher those numbers are, let's say you had a charge of +3 and a charge of -3. Those are going to create a stronger force than a charge of +1 and -1. And that's because the larger the charge, the greater the force. All right, so as we just said, Q1 is particle 1 and Q2 is particle 2. So we're looking at the force between two particles. Now, distance between particles. Notice the distance is in the denominator. What this means is that the distance is inversely proportional to the force. What that means is the farther away the particles are, the weaker the force will be. The closer together the particles are, the stronger the force will be. So farther away the particles, the weaker the force. Right? So, once again, force is proportional to two things. The charges of your particles, Q1 and Q2, the higher the charges of the particles, the stronger the electrostatic force. It's also inversely proportional to the distance. The farther away the particles are, the weaker the force is. And that is known as Coulombs law. So we'll write that right there. Coulombs law gives you the strength of the force between two charged particles and how it depends on the distance between those particles and total charge of those particles. That is Coulombs law. You will just be looking at it qualitatively, not quantitatively. So you just need to know the relationship between force and total charge of the particles and the relationship between force and distance. So you can kind of see down here, we've got two oppositely charged particles. You can think about this as a proton and this is an electron. Protons are positive, electrons are negative. Remember, opposite charges are going to attract to one another. A larger charge is going to create a larger force of attraction. So the more protons you have, the more it's going to attract a negative electron. That means it's directly proportional. And then once again, a larger distance produces a smaller force of attraction. So it's inversely related to distance. So we've got directly related to the charge and inversely related to distance. All right, awesome. So Coulombs law can help us kind of explain a number of different things that we see. The first thing we're going to talk about is atomic radius. The atomic radius is half the internuclear distance between two of the same atoms when the element is in the solid state. Think about a radius like you would in math class. So let's take a look at what happens to atomic radius as we go across a period, and then we're going to do down a group. So let's start by looking at three elements in period 2. So we've got lithium, beryllium, boron, and carbon, and there's pictures of them right here. So notice they are all in period 2, so they have a total of 2 energy levels. Each of these, that's why you see those 2 rings. Each of these has 2 energy levels. Now let's take a look at how many positive protons are in the nucleus. In lithium, we have 3 protons. In beryllium, we have 4. In boron, we have 5. And in carbon, we have 6. So we're increasing our nuclear charge. So 3 protons, then we've got 4 protons, then we've got 5 protons, and we have 6 protons. Remember, those are positive. So what's going to happen? Well, around our nucleus, we have negative electrons. In lithium, we have 3 negative electrons that are attracted to those positive protons in the nucleus. In beryllium, we have 4 protons around that beryllium nucleus that are attracted to those 4 protons. Same thing for the boron, there's 5 electrons around the outside. And then for carbon, there are 6 electrons around the outside. Remember, based on Coulombs law, the greater the charges of your particles, the stronger the force of attraction. And because these electrons are all the same distance away from the nucleus, that means carbon is going to have a greater force of attraction between the protons and the electrons than lithium, which is going to have a weaker force of attraction. So it might help you to add in weaker force right there. So weaker force, and then it gets stronger and greater force of attraction. So what does that mean for the atomic radius? Well, what that means is that as you go across a period, that attraction gets greater and greater, and therefore the radius gets smaller. It gets squeezed. closer and closer together. So for the atomic radius, it's going to decrease as you go left to right across a period. You can think about it like this. We're going this size, and then this size, and then we're getting smaller and smaller. And why is that? That's because the number of positive protons increases in our nucleus, and the number of negative electrons increases in the same energy level, meaning the same distance. So this is Coulombs law, what we just talked about. So let's bring that back. Remember, Coulombs law says that the force is directly proportional to the total charges of your two particles. Since in this, we are in the second energy level, the distance isn't a factor. So the greater the charge of the nucleus and those electrons, the greater the electrostatic force. So that is why they're getting smaller, because those positive protons are increasing. The number of those negative electrons is increasing. That means the force is increasing as we go left to right in the same energy level, so they're getting squeezed smaller and smaller. So that's going left to right across a period. Let's go top to bottom down a group. So now let's take a look at group number 1. We're going to look at lithium, sodium, and potassium. And if we take a look, remember, when we go down a group, we are increasing our number of energy levels because we're going down periods, but we are keeping the number of valence electrons the same. So notice lithium has one outermost electron, but we have 2 energy levels. Sodium has 3 energy levels, and potassium has 4 energy levels. So notice, because we are adding more energy levels, it is making the radius of our atom a lot bigger. So that's the explanation for as you go down a group. The atomic radius gets larger because we have more energy levels. So we're going to go atomic radius increases down a group, and that's because your valence electrons, which are your outermost electrons, occupy higher energy levels. So if you wanted to draw it in a picture, it kind of looks like a little snowman. They get bigger as you go top to bottom. So that's atomic radius. It's the internuclear distance. Remember, it is going to decrease left to right across a period. That's because there is a greater total charge between those positive protons and negative electrons, which causes a greater electrostatic force of attraction, which is going to squeeze your atom closer together. And then as you go top to bottom down a group, your number of energy levels is increasing. So the atomic radius increases. Awesome. All right. Next thing is ionic radius. All right. So ionic radius, very similar to atomic radius, but this time it's the size of an atom when it becomes an ion. Remember, an ion is charged either positive or negative. And we learned this in our last unit. Now, if you recall, on the left-hand side of your periodic table are your metals. So those are things like sodium and magnesium. Sodium has 1 valence electron, so it wants to get rid of that 1 valence electron and become a positive ion. Magnesium has 2 valence electrons, and it wants to lose those 2 to become a positive 2 ion. So your metals like to lose electrons to form positive ions. Now, what happens when you lose electrons? Well, just like when you, in my analogy, lose weight, you get smaller. So the ionic radii of metals are smaller than their atomic radii. And that's due to an empty valence shell, which I'll show you in that picture below. And if it helps you to remember this analogy, you can remember this. I am positive when I lose weight, just like losing an electron, and I get smaller. Same thing when an atom loses an electron, it becomes positive and it's going to have a smaller ionic radius. So take a look at this picture. Here's sodium. Sodium has one valence electron in the third energy level. Then when it loses that one electron and becomes a positive ion, now that one valence electron is not there anymore. And so the electrons here in the second energy level are attracted to the positive protons in the center. And because these are closer than this one was, they are going to pull tighter and have a greater force. So notice you have the same number of protons in the nucleus. Same number of positive protons, and they pull those negative electrons closer to the nucleus. The main thing here is metals like to lose electrons to become positive ions, and when they lose electrons, they become smaller. Let's take a look at your nonmetals. Your nonmetals are up in the upper right-hand side, so those are things like oxygen and fluorine. Oxygen has 6 valence electrons. It wants to gain 2 electrons to have 8. Fluorine has 7 valence electrons. It wants to gain 1 more to have 8. So nonmetals gain 1 or more electrons and they form negative ions. The ionic radii of nonmetals are larger, think about they're gaining something, than the corresponding atomic radii. And this is due to more electron-electron repulsion. Remember, opposites attract, like charges repel. So if you have more electrons, they're going to repulse each other with added electrons. The key that you want to remember here is that weight analogy will help you. I am negative when I gain weight, just like an atom becomes negative when it gains an electron, and I get larger. Just like when an atom gains an electron, it will get larger. So you can see this with fluorine. Fluorine normally has 9 protons and 10 neutrons and has a total of 7 electrons around the outside. Well, if it gains an electron to become an ion, now it has a total of 8 electrons around the outside, and those are going to repel with one another, and it's going to cause that to become larger. So just remember, metals like to lose electrons to form positive ions and get smaller. Nonmetals like to gain electrons and form negative ions and get larger. So let's do some practice. Okay. We're going to look at what ion each of these things forms and then think about, okay, would the ionic radius be larger or the atomic radius? So let's start with magnesium. Magnesium has 2 valence electrons. It wants to lose those 2 valence electrons to form a +2 ion. So the ion it forms is Mg+2. Because it's a positive ion, that means it lost electrons. What that means is it's smaller. So this ion is smaller than the atom. So we would say the atomic radius is what is larger. Let's take a look at fluorine. Fluorine has 7 valence electrons. It wants to gain 1 electron to have 8. Remember, when something gains an electron, it has a negative charge, so -1. So let's compare this to the atom. So remember, when something gains an electron and becomes negative, it gets larger. So that means the fluorine ion is larger than the atom. So we would say the ionic radius is larger. Let's look at calcium. Calcium is in the second group. It has 2 valence electrons, so it likes to form a +2 ion. That means it likes to lose 2 electrons. When it loses electrons, that means the ion is smaller than the atom, so the atomic radius is larger. All right, let's look at lithium. Lithium is in group 1, so it's a +1 ion. That means it lost an electron, which means that it is smaller than its atom, so the atomic radius would be larger. Let's take a look at sulfur. Sulfur has 6 valence electrons. It wants to gain 2 more electrons to have 8, so that would be a -2 charge. That means it gained 2 electrons, which means its ionic radius is larger than its atomic radius. All right, aluminum. Let's figure out what aluminum is. Aluminum has 3 valence electrons. Let's think about what aluminum would want to do. it would want to lose those 3 electrons because that's a lot easier than trying to get 5 more. So aluminum's charge would be plus 3 to show that it lost 3 electrons. Because it has lost 3 electrons, that means its atomic radius is larger than its ionic radius. All right, and oxygen. Oxygen has 6 valence electrons. It needs to only gain 2 more to get that magic 8. So that means it would have a negative 2 charge. Because it gained electrons, that means its ionic radius is larger than its atomic radius. So notice your positive ions, the atomic radius is larger than the ionic radius because they have lost electrons. For your negative ions, like those 3, they have gained electrons, so their ionic radius is larger than the atomic radius. You can see this on the next page, kind of summarized for you, the different charges. Remember, group 1 has 1 valence electron, so we can write number of valence electrons. Group 1 has 1 valence electron, and group 2 have 2 valence electrons. Those like to lose those 2 electrons to form positive ions. So our metals, as we said, like to lose electrons to form positive ions. And then their ionic radius is smaller than atomic radius. Right? Because they lost electrons, they are going to be smaller. All right, then over on your nonmetal side, if you look over here, you have group 15. Those all have a total of 5 valence electrons. Group 16 have 6 valence electrons, and group 17 have 7. So group 15 would like to gain 3 electrons. That's why these all have a negative 3. Group 16 needs to gain 2 electrons. That's why these have a charge of negative 2. And then group 17 needs to gain 1 valence electron. So it has a charge of negative 1. These are all your nonmetals. They like to gain electrons to form negative ions. Because they are gaining electrons, their ionic radius, when they form an ion, is larger than the atomic radius. Awesome. So hopefully this gave you a summary of the different ions that things form, what happens to the size of the radius as an ion forms, and also looking at Coulomb's law and understanding the relationship between electrostatic force and charge, that they're directly proportional, and electrostatic force and distance between charges, which is inversely proportional. All right, thanks.